All right, section 6.3 on trig graphs, trigonometric graphs. All right, we start with y equals sine and y equal cosine. So when we graph, it's just more common to use x and y, and specifically x for the horizontal axis instead of t. So that's just a syntactic change. We're using the variable x now instead of t. Okay, so first time for any graph, it often comes down to just plotting points. And for sine, we've got quite a long table of known values, all the pi over 6, pi over 3, pi over 4 values that we know the sign for. So what's a little bit strange now is that we have been thinking about going around in a circle as we compute values for sine, but now we are going horizontally. The x is on the horizontal axis and just proceeds from left to right, and the y coordinates now get plotted out vertically. So just as an example, when x is pi over 2, the y is supposed to be 1. So here's x is pi over 2, and we're at height 1. And so as we plot all the red points and then connect them up with this smooth curve, we get this graph of sine from 0 to 2 pi. Now we can go beyond this 0 to 2 pi range by just remembering that the values of sine are repeating every 2 pi. And when we get to 2 pi, it's as if we're starting over at 0 again. So in fact, we can write this down as an equation. Sine x is equal to sine of x plus 2 pi. So that's going to tell us that the graph is going to repeat every 2 pi units along the x-axis. So the red part is what we plotted out first, but then the sine graph is just going to repeat every 2 pi units down the x-axis in both directions. Okay, so for any graph, not just for sine, but for any graph that has this repeating property, we say that the graph or the function is periodic, and the length of the x-axis over which that repeat takes place is called the period for the function. So sine x is periodic because it repeats, and it has period 2 pi because it repeats every 2 pi units down the x-axis. Okay, so for a hand sketch, typically, these are all closed up. We're just going to plot on one period, and just remember always that the graph does go on in both directions forever. And what I'd like to see are the minimum number of tick marks here. On the x-axis, we're going to put tick marks at the peak and at the trough of this curve. And at the intercepts. So pi over 2, that's where sine is 1. The highest point, pi, that's where sine is 0. 3 pi over 2, that's where the sine is -1. That's the lowest point. And here at 2 pi, we're back to 0. On the y-axis, I just want to see the tick marks for the low point, the lowest y-coordinate being -1, and the highest y-coordinate being +1. All right, so that's perfectly good hand sketch. Okay, so here comes the second function, cosine x. We'll attack it the same way. Start with a long list of known values here, and just do point plotting. So when x is 0, cosine is 1. So that's the first red dot. When x is pi over 6, the cosine is √3 over 2, a number pretty close to 1. Okay, all the red dots from our table, again, connect them with this smooth curve, and this is the shape of the cosine. Just like sine, the cosine is going to be repeating values every 2 pi. This table just starts over and repeats after you go through 2 pi values on the x-coordinate. When x is 0, we're 1, and when x gets up to 2 pi, the cosine is back to 1 again, and it'll repeat. So the same thing that we said about sine, we say about cosine. We say cosine is periodic and has period 2 pi. All right. So the curves look very similar. The one is really just a shift of the other. Just remember that cosine starts out high, so it starts at 1, goes through a full period and comes back to 1, whereas the sine function starts at 0, goes through a full period and then comes back to 0. Okay. Yeah, so the hand sketch, same things I said about sine. We want to see the tick marks where the cosine is 0 and where the cosine is -1 and +1, the high and low values. And the same thing on the y-axis. Show the small value and the big value for y. Okay, so a lot of this section is about transformations of sine and cosine, and this is similar to what we've done with transformations of all kinds of other functions for exponentials and logs and so on. Once we have the basic graphs, then we look at their transformed variations. All right, I think I'm just going to try to execute all of these commands so these are all open. There it is. Okay, so here's the graph of 3 plus cosine x. All right, so we start with the graph of cosine x. This is lacking because I don't have the tick marks that I want. All right, I hit pause just for a second because I noticed that I was missing the tick marks that I would like to see here, the pi over 2 and the 3 pi over 2. Okay, so the cosine function, remember it's the one that starts high, starts at 1, and ends up back at 1. And all we're doing here is shifting that up 3 units. So the -1 and 1 are going to go up now when we add 3 to between 2 and 4. I typically like to draw a little dotted line for where the shifted x-axis has gone. This is sort of the center line for the curve. Instead of being at the y equals 0, now the center line is at y equals 3. All right, so there's a good hand sketch of 3 plus cosine x. And just my recommendation to do this, not mandatory. Of course, we can multiply by a negative here, and the effect on the graph will be to flip the graph over the x-axis. So here's the graph of minus cosine x. Again, the cosine x here is this ghostly looking function, and the effect of multiplying by -1 is to have flipped that over the x-axis. And there's a good hand sketch. Okay. So we can multiply by -1 and it flips, but when we multiply by other constants, we also get a stretching. So here's the graph of 3 sine x. So the light blue one here, this is sine x with the tick marks labeled. And when we multiply by 3, we vertically stretch the graph. And so the only difference in the hand sketch is now the vertical tick marks are going to be at -3 and 3. For sine x, they were at -1 and 1. When we stretch by a factor of 3, the new high and low points are going to be at -3 and 3. Right, so here's the graph of y equal to half sine x. Again, the light blue one is sine x. And when we multiply by a half, we're going to be multiplying all of the y coordinates by a half. So the graph will now only go from y goes from -1/2 up to 1/2. Oh, that's probably, oh, yeah, so I was going to say that's probably enough. But this one is doing both things at the same time. It's taking the original sign, the negative is flipping that across the x-axis, and then the factor of 2 is stretching vertically by 2. So here's the hand sketch again. So the y tick marks are at -2 and 2. The red graph is what we're plotting as y equals -2 sine x. Okay, so we have a term to introduce here. If you're looking at the graph of a scaled sine function or cosine function, this number out in front, well, its absolute value is called the amplitude of the sine or cosine function. Okay, so you have to make sure that you remember to take absolute value when you answer this question about what is the amplitude of -3 sine x. And this comes up in the reading quiz. So make sure that you remember to take the absolute value. So the amplitude here is 3, not -3. Okay, right, horizontal stretching. So again, we've seen this before. When we replace the x with a constant times x, that's going to affect the graph by a horizontal stretching or shrinking. So when we replace x by 1/6 x, this is true for all graphs, the graph is going to stretch horizontally by a factor of 6. All right, so If you remember just a second ago, sine of x has period 2 pi. So when we get this horizontal stretching, the graph for sine of 1/6 x should have a period that's 6 times bigger. Right, so I'll show you the two graphs. Here's for sine x. And I'm going to click on this button and we'll see the graph of sine 1/6 x. But remember, what's going to happen is that we're going to get a horizontal stretching out by a factor of 6. So this 2 pi is going to stretch out to become 12 pi. And all I'm going to do is multiply all of my previous tick marks by 6. And that will give me the graph of y equals sine 1/6 x. I haven't actually stretched the graph out itself. All I've done is change the scale on the x-axis. Right? So I still want to see these tick marks, the 9 pi, the 6 pi, and the 3 pi, and the tick marks at -1 and 1. So if you remember that we're going to stretch by a factor of 6, all of these tick marks are going to get multiplied by 6. So the pi over 2 is going to be 6 times pi over 2, namely 3 pi. So that's a quick way, I think, to get the hand sketch for sine of 1/6 x. All right, let's try another one. I guess we're going to go the other direction now. Now our constant k here is bigger than 1. So what's going to happen when we replace the x in cosine x by 4x is we're going to horizontally stretch by a factor of 1/4. That is, we're going to shrink down by a factor of 4. Okay, so the period for cosine x was 2 pi. The period for this graph will be only 1/4 of that. So 2 pi divided by 4 pi over 2. All right, so here are the two plots. There's our cosine. Again, it's the one that starts at height 1. The appropriate tick marks, and when I look at cosine 4x, I should take all of my tick marks and divide them by 4. So 2 pi is going to become 2 pi over 4. Pi over 4 is, pi is going to become pi over 4, etc. Right, so there's the hand sketch for cosine 4x. Again, we haven't tried to stretch the graph itself. We've just rescaled the x-axis appropriately. Okay, so there's this general formula for computing the period of a horizontally stretched graph. If we are looking at sine kx instead of just sine x, this graph will have period 2 pi over k. And the same story for cosine kx. Its period will be 2 pi over k. Okay, so one reason is just by what we know about the horizontal stretching of graphs in general. But another reason is, you can think of it this way, is that the graphs of sine kx and cosine kx are going to complete one full period when the kx value goes from 0 to 2 pi. Right? So if we take this pair of inequalities and we solve it for the x, well, how do we do that? Well, we just divide through by the k, assuming k is a positive number. And this may or may not be helpful. If you remember the formula, it's going to be good enough. But what this is trying to tell us, what I'm trying to say here, is that when the x goes from 0 to 2 pi over k, then the graphs are going to go through one full period. By and large, it's good to just have this on a note card. Make sure you remember it. Okay, so we're going to look at combining these effects now. We're going to, maybe I put in a timestamp here. This is just about 15 minutes. We're going to change both the amplitude and period and look at combined effects now. Just one example. Okay, so if we look at the graph of y equals 3 sine pi x, well, first of all, we have to read off the players. The k here is pi. All right, so the period for this graph it's going to be, and this is the formula, it's 2 pi divided by k. So that's going to be 2 pi divided by pi. So the period is going to be 2. Okay, and the tick adjustment, and what I mean by this is that we're going to adjust the ticks for sine x. How are we going to adjust them? We're going to divide by k. Right? So the last tick on sine x is 2 pi. The last tick on sine pi x is going to be 2. So this is true for all of the ticks. We divide all of them by k. And again, here for this example, this is pi. Right? And then we're going to ask, well, what does the amplitude do? Well, the amplitude is a vertical adjustment. Here the amplitude is 3. We don't have to take absolute value. And the tick adjustment, the y tick adjustment, is simply multiply all y ticks by 3. Okay, so we'll do those two things, I guess, separately. So we start with sine x, and then we're going to go to pi x, sine pi x, and all of the tick marks on the current graph, we're going to divide them by pi. Right? That's how we represent this horizontal stretching. So the pi over 2, the new tick mark is going to be 1/2. The 2 pi, the new tick mark, we got to divide it by k, is 2. Right? And then the effect of the amplitude, this number out of 3, simply to rescale the y-axis. So this is our hand sketch for y equals 3 sine pi x. Okay, there's one last effect that we're going to look at, and it's the horizontal shift. So remember, we get horizontal shifts when we replace the x-coordinate by x plus or minus some constant. Okay, so if we replace x with x minus pi over 3, hopefully you remember that the effect on the graph is going to be to shift everything to the right by pi over 3 units. Okay, so we're going to move all of these to the right by pi over 3. So we're going to add pi over 3 to all of them. And the y-tick adjustment, well, none. There's going to be no amplitude adjustment here. Okay, so there's the original graph of cosine x, and this is the graph of cosine x minus pi over 3. Okay, so where did this pi over 3 come from? So in the original graph of cosine x, we don't put a tick mark at 0 because that's the y-axis. But when we take 0 and add the pi over 3, that's where this first tick mark is coming from. And again, that's the high point for the graph. Let me back up and do it just one more time. When we take pi and add pi over 3 to it, let's see if I can do that. That's 3 pi over 3, so I would get 4 pi over 3. That would be the new tick mark. And that's for the trough here. Okay, so that's the graph with a horizontal shift. Okay, so here's everything rolled into one, a nice blue box formula here. We're going to look at sine and cosine. I guess they're shifted, their amplitude has changed, the period has changed. And I'll let you study this blue box from your text. It's things that we've gone over so far, but we'll do 2 examples, and hopefully that'll clarify things. Okay, so we're going to graph this complicated sine function now, or translated sine. We want to read off the players first. So this number out in front, that's the A number. That's -2. And the amplitude for this function is going to be 2. Remember the absolute value. The tick adjustment, and what I mean by that is how are the ticks on this graph going to differ from the ticks on sine? What are we going to do? We're going to multiply the y ticks by 2. The other player we want here is this constant k. So that k is pi over 6. Okay, so it's easy to mistake these numbers. You have to remember that k is not the period. You get the period. I should shut that down. You get the period by taking 2 pi divided by k. So here, oh, this would be hard, but 2 pi divided by pi over 6. That's the same thing as 2 pi times 6 over pi. So that's 12. Okay, the tick adjustment. Okay, so what are we going to do? We're going to divide all x ticks by k equal pi over 6. Okay, let's do those two things first. Or have I? Oh yeah, okay, so I've got them all here. So there's the original sign, and we look at its tick marks. We're gonna combine these first two steps to get the plot of a 2. Sorry, was this supposed to be a -2? Yeah. So I screwed that up. This is supposed to be a -2 here. And this has come simply from adjusting the tick marks, and I guess we've also flipped the sine graph over because of the minus sign here. But because of the 2, the tick marks are now at -2 and 2. We've multiplied them by 2. And the x ticks, we've divided them all by pi over 6. Right? Maybe you should do a quick example of that. So the old tick mark at pi over 2 is now replaced by, this would be a complicated fraction, pi over 2 divided by pi over 6, that's equal to 3. So what was a pi over 2 has now become a 3. Okay, and then the last step here, well, again this is a minus, is because of the x minus 1 here, we are going to shift this graph 1 unit to the right, and consequently we're going to add a 1 to all of the x values as we shift the graph over. Again, this x value of 0 here, when we shift it over 1 unit, we're going to have a tick at 1, and that's where the graph is going to start. Okay, so there's the, I'm sorry if this is hard to read within the code here. This is y equals, oops, I missed something there. Hopefully this will, y equals -2 sine 1/6 pi x minus 1. Okay. One more example. Maybe I'll try to do these one at a time here. The amplitude is 3. Yes, I'm sorry to scroll back here, but something, no, I had this right. The amplitude was 2. I couldn't remember if I had the absolute value taken right. Okay, the tick adjustment, so we're going to multiply y's by 3. Multiply the period. Well, we're going to get the period from having figured out the k. So the period is 2 pi divided by pi will be 2. And the tick adjustment, we divide all x ticks by pi. And the shift, so this is a strange quirk here in the way that our blue box is set up. The blue box is set up as x minus b. So the b here, if we want to be perfectly correct about it, is -1/4. So we're going to add -1/4 to all x ticks. Okay, so we'll do those one at a time. What's the first thing? Okay, multiply by 3 and multiply the y ticks by 3. So that's 3 cosine x. And now we'll work on the pi x. So we're going to put a pi in here. and sorry, I was looking at the wrong line. We need to divide all of our x ticks by pi. So now we're only going to plot out till 2 and all my x ticks by pi. And then the last thing is to add -1/4. This is the horizontal shifting that's taking place here. And so now start the plot at -1/4 and go up, quarter, and go out to 2 -1/4. And this is the graph, the hand sketch of the graph. Okay. Well, let's see, where are we? Kind of running along here, 26. Oops. Mouse by 27. We're going to turn this process on its head and look at it the other way around. Instead of given an equation and coming up with a graph, oftentimes you'll be asked to do this. Given some graph, come up with an equation for it. Okay, so here's a problem from the book. I can't remember if I assigned it, but from the graph we want to read or try to come up with a formula that would produce this graph. Well, because this graph starts out at 0 and goes through a period and comes back to 0, to me it kind of catches my eye that this looks like a sine function that's been shifted to the left. Right, so that's what I've called this. This looks like a shifted sine. Right, so first let's deal with the amplitude. So the amplitude is 5. This graph is going from -5 to 5, so we can figure out that this amplitude is 5. So the next thing to get from the graph is the period. How long does it take to repeat? Okay, well, the period goes from -1/4 to 3/4. So I need to take the difference of those two numbers to figure out the period. It's 1. I mean, we could also maybe just count out 1/4, 2/4, 3/4, 4/4. It took 1 unit along the x-axis to get out a period of this graph. So the period is 1. Okay, to get the k, well, what you have to remember is that the period is equal to let's get the fraction first, 2 pi over k. Right? We just figured out that the period was 1. So that says 1 is equal to 2 pi over k, and that tells me, that k is equal to 2 pi. Okay, and then the last thing to do is to look at the shift. Well, it looks like after the horizontal scaling that the graph has been shifted 1/4 unit to the left. To the left, right? So what that suggests is that a formula for this graph is going to be y equals 5 sine, 2 pi, that was my k value, right? So that's the amplitude and period taken care of. And now I want to do the shift. To get the shift, I need to replace the x with x. I want to go to the left. So I replace the x with +1/4. All right, so do a quick check on that. I guess I can go from the picture here. I won't get my tick marks in perfect spot, but this is the plot that we were going for. Okay. Now this is not a unique formula for this graph. We could also look at this graph and say this looks like a cosine function in that it starts out at height 1 on the y-axis. But it looks like a cosine function where we didn't plot from 0 out to 1.25. Instead, we started our plot just a little bit further to the left. So this is totally optional, but I wanted to show you that there is more than one way to view this. If we view this as a cosine function, Well, the amplitude is still 5, and the period hasn't changed. So period 1, and the k, right, it's still 2 pi. So that reasoning as before. But now we say for the cosine function, there's no shift. We're not shifting the cosine function. All we're doing is shifting where we choose to plot it. So y equal 5 cosine 2 pi x should also be a formula that gives us this graph. But again, what we're going to do is plot it. I wish that I wouldn't get those pop-ups. I don't know what's making that. We're going to plot it from minus 1/4 to 3/4. Okay, so we get the same graph this time using a cosine function. So we'll talk more about this in class, and I'll try to give you feedback on team quizzes and maybe some of your homework. But when you do hand sketches, by and large, this is what I'm going to be looking for. Tick marks at the start and end of a period, and at the crest and trough, the high point and the low point of the sine or cosine, and then the y ticks at the high and low point. Okay, examples 7 through 10 out of your book. I'm skipping those. You're welcome to look at them over if you like, but we're not going to deal with variable amplitude, which is what those are covering. All right, that's it for today.